This is the 14th lecture of the course MTH 204A for section B. Recall that in the last lecture we were talking about the actions of general linear groups and some of its important subgroups on the space of all bilinear forms. So, in the last lecture we talked about orbits. In this lecture we will now start with the stabilizers of these actions. So, we will see that very many important subgroups of GLN in the concrete situation of Rn or Cn, GLN R or GLN C appears as the stabilizer of some bilinear form or quadratic form. So, example. So, consider this for the on the vector space Rn, consider this form x1 y1 plus xn yn. This is the bilinear form where x1 up to xn and y1 up to yn, these are vectors in Rn. So, okay, so before that let me remind you, given a bilinear form on a vector space V, by stabilizer I mean that it is the following subgroup. So, for P belongs to GLV such that f of P x Py is f of xy for all x y in V. Okay. So, here this one is basically it is to be written if you want to write it in the x transpose y. So, if an invertible matrix that preserves this, that you must have x transpose A transpose A y, that has to be x transpose y for all x y, and that implies A transpose A equal to identity. Similarly, A in transpose will be also identity, and from that we obtain that this is the stabilizer of this form is this orthogonal this ON then by n orthogonal matrices. More generally, if on let us say n, so let S and R are non-negative integers such that S plus n equal to S plus k equal R equal to n, and consider the following form x1 y1 up to xs ys, and then just the negative of the rest. So, x s plus 1 y s plus 1 x x y s plus 1, and then finally x n y n. So, better to put that in the matrix notation x transpose. So, the matrix of this will be just is minus ir y. So, this is a bilinear form on Rn, and the stabilizer of this bilinear form is called the stabilizer is called the general orthogonal group. Stabilizer is called the general orthogonal group and denoted by OSR. Okay. So, you can, the reason for calling it the general orthogonal group is when S is 0, then we get the orthogonal group of matrices. Okay. Another important group that comes along this line is the following, that if we take our matrix to be the following, the matrix of the bilinear form In and I minus n, if this is my matrix of the bilinear form, so how will it look like? You can write down the expression for that. So, basically the first n vectors will be multiplied to the first n components of x will get multiplied to the corresponding last n components of y, and the last n and the first n components of y will get multiplied to the last n components of x. So, and in this case the third example, first, more generally second, the third example, here the stabilizer is called the symplectic group. stabilizer is called the symplectic group and denoted by SP and F. Remember here you do not have it could have been over any F, you do not have to consider F is equal to R or C. Over any field you can talk about this symplectic group of order n of symplectic group symplectic group SPn over F. Okay. So, remember the form is on F to n. Okay. Then the fourth example is regarding quadratic forms. So, let Q be a real quadratic form on Rn. Q be a quadratic form on Rn, then what is the stabilizer group stabilizer of this quadratic form? So, remember that a quadratic form is necessarily given by some symmetric matrix. Okay. So, by a stabilizer, by a invertible matrix stabilizing this quadratic form, it means that P transpose AP has to be P, right, because stabilizing means Q of Px is Px. So, if for some P Q of Px equals to Px for every x, then from that this is what we obtain. So, therefore, stabilizer group is the invertible matrices such that P transpose well, I mean, in order to talk about P Q, then even for this bilinear maps it should come with P inverse, but since we are talking about since this is going to be a subgroup, so writing P inverse throughout is P inverse here is same as writing P here, because we are in a subgroup. So, such that P transpose AP is equal to A, okay, and is a symmetric matrix. So, given any quadratic form, so its stabilizer. So, well, before that also I would like you to note that given any quadratic form, let this be expressed by this. So, the corresponding bilinear form so given a quadratic form, from that we can immediately talk about a symmetric bilinear form given by this. Okay. So, you see that so the stabilizer of this quadratic form is same as the stabilizer of the corresponding bilinear form, okay, because it is given by a matrix. Okay. So, because yeah, the main point is that for any symmetric matrix, this is what you can, I mean, you can convince yourself in that for any symmetric matrix, matrix let us say B. So, x transpose by equal to 0 for odd xy in Rn is same as saying x transpose Bx is 0 for every x in Rn. Okay. So, from that you can immediately convince yourself that if something stabilizes this the stabilizer of this quadratic form and the stabilizer of the bilinear form, they are the same. All right. So, given any quadratic form, this stabilizer is called the orthogonal group of that quadratic form. The reason for calling it orthogonal group is very simple. If this is my quadratic form, then we see that from just what we have observed, its stabilizer is nothing but the stabilizer of this bilinear form, which happens to be the orthogonal group of matrices. So, keeping that analogy in mind, we define the notion of orthogonal group in the generality for any quadratic form. So, I repeat, in particular, when the x1 square up to xn square is the required quadratic form, then that corresponds to our known orthogonal group. Okay, so maybe I should leave this as an exercise to here, exercise to you, because we have talked about general orthogonal groups and all this. Okay, so before that maybe I should do another example. So the fifth example is, so here the vector space was Rn, it was over any f, this is again Rn. So now let us take f equal to c. Okay, now let us make f equal to c, and then what you can do is on c also you can take the same form, this bilinear form. So as expected, then what we are going to get, the stabilizer is this all matrices, complex matrices, such that A transpose A equal to A transpose equal to identity, right. So this is called ONC, which is called the complex orthogonal group. Remember, that is not same as unitary group. Okay, since I am talking about complex orthogonal groups as well, it also makes sense that I mean if the real orthogonal group comes as the stabilizer of some bilinear form, then it's also not quite difficult to guess that or ask the question, thus can the the group of unitary matrices form in that way? Yes, that happens, but for that we need to change it a little bit. So let me put it as a remark here. So if V is a complex vector space, then by a conjugate linear form, some people call it semi-linear form, or not semi-linear, something else, I cannot exactly remember, but for the timing let us call it a conjugate linear form. By a conjugate well, conjugate may be bilinear form, but do not confuse that with the usual bilinear form. The reason for using the word conjugate will be quite clear to you now. So by a conjugate bilinear form, I mean a function of this kind, such that f is linear in the first variable, and for the second variable we must have the following, that x y1 plus lambda y2 is f lambda conjugate f x1, sorry, I should put it in this way, f x y1 plus lambda conjugate f x y2. Okay. What is an example of this conjugate linear form? Take V to be Cn. So the form will be Z1 W1 bar Zn Wn bar. Thus you can see that so this is basically the usual complex inner product. So this you can regard as the generalization of the usual complex inner product. For complex inner product, one conjugation comes from the second component. So like earlier, so given such a form, it's stable. So GLNC, it's easy to see that like earlier this acts on the space of all such forms. Okay. Then of course here the analogues of symmetric forms will be the Hermitian forms. So we do have actions of GLNC on the subcollection of Hermitian forms. So the analogous questions that we have done, we have dealt with for bilinear forms over I mean what we have done in the over R, those questions can be asked here and can be dealt with, and therefore I leave the entire thing to you as an exercise that you should investigate what happens to their analogues for in such case. The interesting point is regarding this unitary group is the following, that if this is the form, then what is its stabilizer? You can easily see that the stabilizer of this form is the stabilizer is maybe I can write it in this way. So, this is nothing but Z conjugate transpose, yeah, conjugate, yeah, this is what it is. So, the stabilizer is, you can easily see, stabilizer is the unitary matrices. Okay. Now, come here. So, this was just I put as a remark. Now, come to the genuine case of original case of, not original, what we are earlier dealing with, the case of bilinear forms in the sense we have defined earlier. So, here we have talked about orthogonal groups, general orthogonal groups and complex orthogonal groups. So, in this context I would like to give the following exercise to you, that somehow as the stabilizers of non-degenerate forms, only these groups will appear. So, let me put it in this way. So, suppose F is R and V is having dimension n, then the stabilizer of any non-degenerate bilinear form. Remember, non-degenerate means corresponding matrix is invertible. Non-degenerate bilinear form is isomorphic to ORS, where as usual R and S are 0, R plus S equal to N. So, the first exercise says that if the form is non-degenerate, of course on a finite dimensional vector space, then stabilizers will be nothing but these generalized orthogonal groups. And the second question is of course is complex analog. If F is C, then the above is that is for any non-degenerate bilinear form, the above is isomorphic to complex orthogonal group. So, on finite dimensional vector spaces over R or C, if we take non-degenerate real forms, then as stabilizers we are going to get this kind of groups, namely either in case of R we will get real generalized orthogonal groups. In case of C, we will get the whole complex orthogonal group. Okay. Anyway, so we should now move on to other actions. So, now I should talk about the actions of affine general linear groups. So, as expected, we let F to be Q, R or C. We let F to be Q, R or C, and of course, we do have action of AGLV on V. This action is transitively, unlike that of GLV, because here you are allowed to translate. So, this is transitive, and when we do, the dimension is finite, and of course, let us get at least 2, then we can then the action of SL, SLN, SLV is also transitive. Then in this transitive actions, what are the stabilizers? So, here what is the, so is the transitive action, right. So, what is the stabilizer of the origin 0? So, of course, if it is stabilized, then then the transformation is not allowed to translate. So, therefore, the stabilizer of origin in both the cases, stabilizer of the origin, well, I should put 0. Stabilizer of origin is in the first case it is simply GLV, and in the second case it is simply SLV. Okay. Then furthermore, if V is finite dimensional, V is a finite dimensional real inner product space, real inner product space. Then of course we have the group of all isometries of V acting on V. This is also transitive by the similar logic, and here the stabilizer of origin is precisely the orthogonal group of V, because we have a concrete description for this isometric group. Okay. Set of all orthogonal transformations on V. And this affine linear, affine general linear, affine special linear group that acts on this group acts on the collection of affine subspaces only, affine subspaces as well. So I mean let's take everything finite dimensional, and Sk be the collection of all affine subspaces of dimension k. Therefore, we can now this AGLV acts on Sk as well. Okay. So what about this action? It's easy to see that this action is transitive. Because I mean if you take any two k dimensional subspaces, then there is a general linear map sending one to the other, right? Now for the rest you just have to take care of the translation part. So therefore this action is transitive. Similarly in the case ASL, of course we do have ASL2, ASLV acts transitively, and then when we have inner product, then we will get the isometric group that also acts transitively. Okay. Fine. Yes, and yeah. Since it's transitively, so in order to talk about the stabilizer, it's enough to talk about the stabilizer of the yeah. So to have a concrete visualization, maybe what you can do is in order to see things concretely, we can take simply V to be Fn. Let's take V to be Fn. Then we let's call this, consider this subspace Wk to be the span of E1 E2 Ek. Okay. So then what are the transformations? So what's the stabilizer of this subspace under right? The stabilizer of this subspace has to be of the form that first of all, so a typical element in this GLV, that will be of the form some TV times A. Okay. So TV times AW, it has to be W. So what is this? This is nothing but V plus AW, right? V plus AW is W. So that immediately forces that. So the right hand side is a subspace, the left hand side also has to be a subspace, and from that it forces that the AW will be W and V has to belong to W. These are the two conditions have to be there, and from that you can you got the stabilizer. So AW is W is so here you know the matrices, right? So if you want to view that inside GLN plus 1F, so in the first n by n block we have the first k, for the first k columns we may have something, but here the rest will be 0, the k columns, yeah. So these are the k vectors. then the rest will be simply 0, and then then of course there could be anything here which you do not care, again this is 0, and the last column can also go up to the kth portion, okay. And here as usual we will have 1, here you will have 0. So, the all matrices of this form. So, similarly you can do for the other groups. Now, I should move to other actions. When V is a finite dimensional vector space, inner product space, then as we have earlier seen that the group of all isometries that acts on the collection of all open balls, collection of all closed balls, collection of circles. So, what about the orbits under those actions? So, it is easy to see that if we start with an open ball with radius r, then its orbit consists of all open ball of radius r. The same goes for closed balls, because isometric group that preserves the distance. Similarly, all circles are, if I take a circle of radius r, then in its orbit all cycles of radius r will be there. The situation becomes somewhat more maybe the case when V is, in addition to that, V is R2. In this case we have much more concrete description which we are familiar with. So, if V is R2, then what is isometry group of all isometries of R2? So, what are the isometries of R2? So, they are of this form, that some orthogonal transformation on R2 followed by a translation. An orthogonal transformation of R2 is either a rotation or a reflection, right, and then it is followed by a translation. So, suppose we have two figures which are in the same orbit of under the action of this isometries of R2, then what does that mean? Taking one figure by applying translations, rotations or reflections, I can manage that, I can superpose that onto the other figure so that they exactly match, okay. That is what we call in our school geometry, that is what we call in our school geometry as the figures are congruent. So, thus in this case, let us say two triangles, they are in the same orbit, that means they are congruent. Similarly for quadrilaterals, similarly for parallelograms. So, thus in this situation what we are familiar with in our school geometry, in our school Euclidean geometry, this is just in this case this is just another way of expressing that in a different or more sophisticated language of group actions. But in this situation it is just talking about our old congruence and nothing else, okay. But however, this language of group actions, or these are quite general as we are talking about, okay. All right, let us now move to some other kind of actions. So, what kind of other actions we can think of on any vectors? If F is Q, R or C and V is a vector space over F, then earlier we have seen that the additive group of F acts on V in the following way, that is, we fix a non-zero vector. If we fix a non-zero vector, then it moves each V to this, okay. So, here what are the orbits? So, starting with any V. So, starting with any V, what we can see is, so here the group is F. What we can see is we get the entire line passing through V in the direction of W, okay. So, thus here each orbit is a line in the parallel line in the direction W. So, hence in this case you can say that in this case you can say that the orbits are the parallel lines, parallel lines in the direction w, or lines parallel to, let us say, f w, the linear span of w. Let us now go to talk about another example. Recall that this group Z mod 2Z has a natural action on Sn. Sn is the n dimensional sphere. So, for any given x in Sn, what is the orbit of x? It is easy to see that the orbit of x is x and minus x, right. That is how the action is defined, that the class of 1 acts as sending each x to minus x. So, therefore, for each x this is the orbit. So, what about before that I think I should make a general definition that if G acts on x, then the orbit space if you are not comfortable about the word space, so you may just ignore it. So, here it is just a name. The reason for calling it a space will be clear to you later on. So, the orbit space is nothing but the collection of all orbits under this action. Of all orbits thus just a collection. So, some authors denote this by this. Slightly have to be careful that it is to be distinguished from the set difference. So, G is written slightly downwards. So, the reason for introducing this terminology is simply that the same reason for which I keep on using the word space is later on you will see that in topology many interesting topological spaces will arise as the orbit space under the action of some group. So, here let me just give you an instance, and with that I will be completely moving to some other topic related to group actions. So, geometrically, so let this be the n dimensional sphere. So, if x is here, then let us say x is here, then its orbit another point in its orbit is minus x. So, for each x, if we think of joining so x and minus x are the diametrically opposite points. So, if we join any two diametrically opposite points by a unique line that exists, right, given any two diametrically opposite points we have a unique line. So, in that way we have a natural identification of the collection of all such orbits, that is the orbit space under this action. The orbit space under this action and the collection of all lines in Fn plus 1, right, because any line will intersect. So, given any line in Fn plus 1, certainly that will correspond to two diametrically opposite points on this sphere, unique correspondence. So, given any line you have a unique pair, and given any pair of diametrically opposite points we get a unique line. So, thus we have a correspondence, natural one-to-one correspondence between this orbit space and the collection of all one dimensional subspaces of Fn plus Rn plus 1. So, the later is called PNF, PNR, right, in Rn plus 1 all one dimensional subspaces. And so, yeah, so you have a natural identification one-to-one correspondence between them. So, thus this orbit space here can be naturally be regarded as as this projective n space over R. And another interesting identification here is also the following, that let's consider the action of the group R minus 0 on Rn plus 1. Okay. So, what is the orbit space here? What are the orbits here? So, it is easy to see that the orbits are the lines passing through origin, but punctured at the origin, right. such the lines passing through origin, the punctured at the origin. And again, so any such punctured line naturally corresponds. I mean, if we map any punctured line to that corresponding line, then any such punctured line, if we map that to the corresponding line, then we have a very natural bijective correspondence between the odd bit spaces under this action to the collection of all lines in Rn plus 1. So here also a completely different, so here it is just 1-to-1 correspondence I should written, and here the acting group is this, acting on Rn plus 1. So different groups, different spaces, but we do have a natural correspondence between their odd bit spaces, right. So this is quite clear that we are sending in punctured line to a corresponding line, we have identification between this and this, and we had something between them. Yeah, so I think enough of odd bits and stabilizers. In so many examples, concrete examples we have seen, we have found odd bits and stabilizers. Now let us move to something else. So before we move to something else, let us do one more thing related to odd bits, but not of course finding the odd bit in some concrete in some example. So it's more like something general. So this is called the Burnside's formula. So assume that so G is let us consider a finite group G and acting on a set X. X is also finite. So this is just a count. This so Burnside formula is about the number of odd bits under such an action. So it's a counting formula. So in order to motivate ourselves, of course things can be formalizable. So let us view that in this way, that consider a table. So here let us write, so here on the top let me write down the points in the set X. Let us write that by x1 x2, and let us write down the groups elements of G by G1 G2 G3. Let us draw a table, okay, and what we do is, given any G in G and X in X, if G of X is X, that is if G fixes X, then in that box we will put a tick. So suppose here, for example, if G is identity, if G1 is identity, then certainly we have to put tick to every such box in the first row, because identity fixes anyone. And suppose let us say G2 fixes X2, then I will put tick to, I will put a tick here and leave other boxes blank. So thus, given an action, I can form this table. I can form this table. And the question now I am going to what I am going to do is, I am going to count the number of such ticks in two different ways. So in what are the different ways? Either you can count the number of ticks appearing in each row and then finally some take their sum, or I can do it column wise. So let us do, and of course I have to arrive at the same at the end. So what is there in a typical row? So for any G in G, let us define Fg to be the number of x's fixed by G, that is number of fixed points of G. So number of x's, okay. So thus the total count of ticks is nothing but, so this is just the row wise count. And similarly column wise, so let us, what is the first column? So how many ticks are there in the first column? That is number of group elements which are fixing x, which are fixing x1. So that is exactly the order of its stabilizer. So in each column, the number corresponding to x in the column, in its column, the number of ticks is exactly the order of its stabilizer, okay. So thus column wise we must have Yeah, so the order of stabilizer of X. X is in X, okay. All right. So this is what we must have, and now let O1 up to OK, O1 up to OK are all distinct orbits and of this action. Orbits under this action. Okay, these are all distinct orbits, and then once therefore this now can be written as, because why are we dividing that? Because if two x's are in the same orbit, then their stabilizers will be conjugate, therefore the order of their stabilizers will be same. So thus we can write the above one as follows: I from 1 up to k, then x belongs to y, stabilizer of G in X, okay. Because when 2 points, for every point lying in the same orbit, the stabilizers, the order of their stabilizers will be the same. So therefore, so basically for these many, for order of y number of times, this summand is being repeated, this quantity is being repeated. All right. Then so now this is quite clear to you what is going to happen here. So as usual we have from I from 1 up to k. So in this, so for each x here this quantity is the same, thus therefore we must have stabilizer of x in G times order of this orbit, right. So okay, yeah, stabilizer of this quantity, order of this orbit, yeah, because this sum is nothing but the same quantity is being repeated number of order of y times. So stabilizer of x, its order times number of times order of y, and by orbit stabilizer theorem that product is nothing but precisely order of G. So thus the entire sum is k into order of G, therefore so this is being equals to this, so thus k, that is the number of orbits, is nothing but the following average. This is called the Burnside formula. It says that when things are finite, then the number of orbits is nothing but the average of the number of points fixed by the elements of the group elements. That is what it says. It has some corollaries. These are also quite interesting. Of course, these can be determined in different ways, but as a corollary of Burnside's theorem, they are simply immediate. So the corollary 1, okay, corollary 1, if x has at least 2 points, x is a finite set, and of course G is finite, so I do not bother to write that again. So assume the setup is the previous one, otherwise we cannot talk about this Burnside's formula. So here just the assumption is x is not singleton, and furthermore the action is transitive. Action is transitive. Then what does this formula say? So this is 1, right? So from Burnside's formula we must have, this sum I can break it into 2 ways. So the first one is Fe, F1, 1 is the identity. So F1 is same as x plus then other Fg's for the non-identity group elements, okay. And yeah, so one thing is very clear that from this one size formula. So, how many terms are we are having here? Exactly same as this, right? If so, and the average is 1. So, and this term is already at least 2. If all other terms here are at least 1, then certainly average will be greater than 1, because this term is at least 2, each other term is at least 1, and so therefore the sum here is at least order of g plus 1. So, the average is not going to be order of g. If each for each non-identity g, this is at least 1. I repeat that if for all g not equal to 1, if g is at least 1, then the RHS is strictly greater than 1, which is a contradiction. So, that means there must be a fixed point. There exists a g, there must be a not a fixed point, there must be g fixing no point of x, because if g is empty means g is not fixing any point. In g. And as a further corollary to that, we can have the following, that let G be a finite group, H is a subgroup of G, proper subgroup, then G cannot be equal to the union of all conjugates of H. G cannot be equal to the union of all conjugates of H. Why? That is quite clear, that the reason is you consider the action of G on G modulo H. Okay. Since H is proper, here this set will have at least 2 points, and then use the previous corollary. Okay. So, of course, this can be deduced otherwise, but perhaps by means of one size formula this is immediate. Anyway, so now let us move on to, okay, so we have done enough of orbit stabilization, we also counted the number of orbits. Now we may move towards applications of Sylow's theorem. Sylow's theorems have already been proved, but before that I would like to spend some time on P groups. So what we mean by P groups is fix a prime P. If a group is said to be a P group if its order is some prime power P. Let us say some prime power P for some any n. So groups of such order are called P groups. So what do we know about P groups? Already we have deduced the following, that for P groups the center is trivial, center is non-trivial, and furthermore not only center, if I take H to be a non-trivial normal subgroup of G, then that also intersects the center non-trivially. In fact, the order is at least P. In particular, when H is having order P, then H will be contained in the center. So, in fact, so we have also proved a general something, a generalization of that for any group. If P is the smallest prime dividing order of G, then any normal subgroup order P is contained in the center. And then what further is true, which we haven't deduced, which we will prove now, is suppose H is a normal subgroup of G. Suppose that H is a normal subgroup of G, then for every divisor of order of H, there exists a normal subgroup, of G which is contained inside H and having exactly that order. Okay. So, corresponding to every divisor of order of H, we have a normal subgroup of G which is contained inside H with that order. In particular, when H is the whole of G, thus we find that corresponding to every divisor of order of G, we do have a normal subgroup of that order. So, when again let me repeat, when H is whole G, then we find that for every group, for every divisor of order of G, we have a normal subgroup of that order. So, proving the last one is again a quite the argument is a very similar one. We run induction. For that we need to make the order smaller, which is done by means of quotient, considering the quotient. So, yeah. So, how do we do it? So, let Z be a normal subgroup of Z be a normal subgroup of so, and Z is having order P, cyclic group of order P. This exists because like if H is trivial, then there is nothing to do. If H is non-trivial, yeah, so if H is non-trivial, here p to the power b, yeah, so here you can take H to be non-trivial, that is not an issue. If H is non-trivial, then this has order at least P, okay. So, therefore, certainly we can pick up an element having order P from this, and this is the cyclic subgroup generated by that element. So, the upshot is we can find a cyclic subgroup in between cyclic subgroup contained in both H and center of G, since it is having P contained in, yeah. So, yes, so here if H is non-trivial. Now, let us consider the order of the factor group. This is certainly p to the power n minus 1, because this has order P by induction hypothesis. So, H modulo Z, so it makes sense to talk about H modulo Z. So, H modulo Z is subgroup of G modulo Z, right, is a subgroup of G modulo Z. It could be trivial if Z is exactly H, that could be trivial, but in that case you actually do not have anything else to show, because then the subgroups of H are exactly trivial one and H itself. So, if this is non-trivial, so I think let me say that if this is trivial, then you do not have anything to do. If this is non-trivial, then we use the induction hypothesis. So, this is a P group, this is a subgroup of that, then corresponding to every divisor of this. So, let me put it in this way, let p to the power b divides order of H modulo Z. By induction hypothesis, we do have a normal subgroup of G modulo Z. How does a normal subgroup of G modulo Z look like? It will be of course of this form, where n is a normal subgroup of G. So, we do have a normal subgroup of G modulo Z. Normal subgroup of G modulo Z, and this is also contained inside by induction hypothesis H modulo Z. Okay. So, this shows that H is contained in n is contained inside H, n is contained inside H, and what is the order of n? Order of n will be okay, and this n modulo Z is order having this order p to the power b. So, therefore, it shows this, and n is order of n is simply p to the power b plus 1. Okay. So, what do we have? Therefore, for every divisor, for every p to the power p dividing this, we got a subgroup of n of order p to the power b plus 1. Okay. So, this list of n's together with the trivial case, that is Z, gives us the complete list of subgroups of this. and here Z has to be normal because it is inside the center. So, let me again repeat, for each divisor p to the power b of this, we have a subgroup of the b plus 1. So, those are the subgroups that we obtained having order p square, p cube, something like that. So, that the subgroup of order p is not counted in this list, and the subgroup order p is precisely this Z. So, this ends together with Z gives us the complete list. Okay. So, I will just say one more thing and then finish this lecture. In the next lecture, I will continue from that. So, I say that as a corollary of, I think we can make it as a proposition, every p group is nilpotent. Every p group is nilpotent. How to show that? That is easy. Every group is nilpotent. The way to show this is very simple. So, for that what we have to do is the following, that for nilpotent we have to talk about we have to consider the ascending central series, the upper central series. So, let us take Zg, this is non-trivial, then we consider G modulo Zg. So, its center is again, if this is trivial, then you do not have anything to do, you are done. If this is non-trivial, then again its center is non-trivial because it is a p group. Then when you pull it back, that will be a subgroup of G containing Zg properly. So, therefore, in this case you get this. Now, again you consider G by Z to G. If this is trivial, then you are done. Otherwise, you can take its center which is non-trivial. When you pull it back, it will be a subgroup of G containing Z to G properly. So, proceeding in this manner, so you have to stop somewhere because a finite group, and once it stops, it has to be all of G, because we have already seen that if whenever upper central series stabilizes for a finite group, then I mean whenever, yeah, so upper central series, yeah, so of course, yeah, fine. So, it has to stabilize, and it cannot stabilize at a very proper stage, because if it stabilizes, let us say from the nth stage, then if Zn, if this is not G, then again we can consider this group. So, that will yield a further proper subgroup of, I mean further subgroup of G containing this one properly, which is not allowed because we have assumed from the nth point onwards the chain stabilizes. So, whenever it stabilizes, it has to be exactly G. So, this shows that G is nilpotent. Okay. So, maybe more formally you can conclude this by induction, but however this is what this is exactly how the argument is going on, that is unless a term becomes G, we can always produce, we are always able to produce a bigger term in the next term, in the upper central series will be certainly bigger than that. So, and since the group is finite, it has to, this has to stop, okay, and this is when it stops, it has to stop with G itself. That is what we have argued. Okay. So, I think with that I will finish this lecture.